Okay. Good afternoon, everybody. So, confidence intervals for two populations. We have started with the case that we know the variances for two populations, and we use basically Z distribution to come up with lower and upper confidence interval with 1 minus alpha confidence. Then we had example in cases that we don't know the variance, then we have two scenarios. The first one, we assume the variances are unknown, but they are equal. So in this case, we can use the pooled estimate of variance, which is basically weighted average of single variance estimates, or like each population estimate, as you can see. And then use that one, combine it with t distribution, because we know that this quantity here, which is a standardized mean difference with respect to the pooled variance or pooled standard deviation, follows a t distribution with n1 plus n2 minus 2 degrees of freedom. And we said basically we can use this t distribution to get lower and upper confidence interval when n1 plus n2 minus 2 is greater than 30, then your t distribution can be well approximated by z distribution. In cases the variances are unknown, we use basically another set of confidence intervals. It's not exact, it's approximate confidence interval, and that's why the degrees of freedom is something in this form. Okay, so the degrees of freedom depends on the sample size as well as basically the sample variances for each population. And as you can see, it's very similar to the Z basic confidence interval. We just replace sigma squared with S1 squared, sigma 1 squared with S1 squared, and sigma 2 squared with S2 squared. Okay? Any questions so far on confidence intervals? Then we talked about the ratio of the variances. So the confidence interval for the ratio of the variances, and we use this basically well-known equality which shows the relationship of f alpha and f1 minus alpha. And these are basically two one-sided confidence bounds, and this is one two-sided confidence bound. And S1 squared and S2 squared are sample variances for the two populations, and F is found from the chart, F chart. And we had a couple of examples. The last one is confidence interval for difference in population proportions, and as you can see, with large sample size. So this is only valid, this is sort of approximate and only valid when we have large sample size, because we are using central limit theorem in that case. Okay, so we have two populations, and both of them are Bernoullis. So first one is P1, second one is P2. We collect a sample of x1 up to xn1. These are Bernoulli observations. These are parts, say, good or bad, conforming, non-conforming. Or these are basically any variable with two possible outcomes. We calculate x bar, and this x bar is called p hat 1, which is estimate of your p, point estimate of your p for the first population. We have another sample which is independent of the first sample. This is very important. Again, two samples should be independent. Independency within sample as well as independency between samples. And we calculate y bar, which is the estimate for the second population. And we know that both x bar and y bar are between 0 and 1. These are sort of like ratios or percentages. Okay. Then what we can do, we know that p hat 1 minus p hat 2 follows a normal distribution with mean P1 minus P2 and the variance of basically the combination, okay, which is P1, 1 minus P1, and 1 plus, actually this is the standard deviation. Let me show the variance. Where is that razor? That's the standard deviation. This is the variance. So you remember, we had x bar minus y bar. Then it's mu x is normally distributed with mu x minus, or mu 1 minus mu 2 plus sigma 1 squared divided by n, sigma 2 squared divided by n. Remember that? That's the same thing. P1 minus P2. This is the variance for the Bernoulli population divided by the sample size. Variance for the second Bernoulli population divided by sample size. Okay? Then this is basically mean and variance. We can easily, actually this is with no estimate, then we can estimate that. If we estimate it, we can say P1 minus P2 minus mean, this is the average, divided by a standard deviation, which is the estimate of the standard deviation. When n is large, both n's are large, follows a normal distribution with 0 and 1, which is a standard normal distribution. Then based on that, we can find this lower confidence interval and upper confidence interval. Is it clear? Again, we don't know the variance. That's why we are estimating the variance by p hat 1, 1 minus p hat 1, and p hat 2, 1 minus p hat 2. Any questions? Yep. Yes. So it's like two populations, two different populations. You need to have one independent sample from this population, one independent sample from that population. That's it. No. It could be between. Okay, put it this way. Let me give you one example of dependency. Let's say you are using let me give you a good example of dependency. Yeah. So let's say you want to compare the performance of two measurement devices, okay, or two operators in terms of measurement. Then what you get, you collect a sample of data. You ask operator 1 to measure those basically parts. Okay, it gives you x's, these x's. Okay, and then you ask operator 2 to measure those parts, which gives you y's. These are dependent. Why? Because you are using the same parts. Although you have two populations, which is measurement, two different samples from two populations, which is the measurement from operator 1, the first population, and measurement from operator 2, which is the second population. But these two data sets are dependent. Why? Because you are using exactly same parts. Does it make sense? That's basically the one example of dependency. Otherwise, if the population has nothing to do with them, just collect a random sample, then it's going to be random. I mean, like independent. Is it clear? Okay. What else here? I think, you remember I said like n1 plus n2 minus 2 should be greater than 30, that you can estimate like approximate t with z. Here, both n1 and n2 should be large. It's not n1 plus n2. Both of them should be large. This is very important. Over there was like the summation should be large. Here, both of them should be large. Why? Because I'm using the approximation to normal for each of them. I assume that each of them can be well approximated by normal. So both ends should be large. Any questions? Is it good? And this is one-sided, which is very similar. You just replace Z alpha over 2 with Z alpha. So one example here, we have crankshaft bearings, and we have a modification in the surface finishing process, and we want to see basically this modification before or after has an advantage or not. So what we do, we collect a second random sample of 85, and the number of defectives are as follows. For the first one is 85, and p hat is 0.12. I think it was a previous example. If I go back, oh, I don't have it here. It's for one population. It's another lecture note. The single confidence interval for single population. But anyways, so for the first sample or first population is, this is the p hat that I have. And for the second one, I have again 85 observations, and p hat 2 is 8 divided by 85, which is 0.09. So basically I have current process, improved process after some modification. I want to see if the improvement basically helps or not. Okay? You can see there's a modification. So what do I mean by helping or not? If it helps, I expect that the population ratio should be what? The percentage should be smaller. Okay? So if it helps, I expect that the second, the ratio for the second population to be smaller than the first one. This is current process. This is improved process. Okay? As you can see, based on the point estimate, okay, this is better than the other one. Okay, the improved one or modified one is better than the original one. But the question is, can I claim this statistically? Because I know that I cannot rely on point estimates. I need to use a confidence interval to draw a statistical conclusion. Does it make sense? Okay. Now, what should I do? I want to find a confidence interval, which is this guy, plus minus and 1 and 2, which is in this case 0.12 minus 0.09 plus minus 0.12, 1 minus 0.12 divided by 85 plus 0.09, 1 minus 0.09 divided by 85. And you get u equal to minus point, is it minus? It's weird. Oh, I'm sorry, I forgot the z alpha over 2. And alpha here in this example is 1 minus alpha is 95%, and your alpha is 0.05. Alpha over 2 is 0.025, and z alpha over 2 is 1.96. So it's 1.96 here. And if you calculate this guy, you will get L as negative 0.06, and U is 0.112. Any questions? Is it clear? Just plugging the numbers. Okay, so what is the conclusion here? Is the modification that we made in the process helped? Has it helped or not? We cannot tell. Why? Because it's basically one is negative, the other one is positive, which like 0 is in between, so I cannot say P1 is greater than P2 or P2 is greater than P1. Okay? If both of them were basically positive, then I would say the improvement was effective. Okay? If both of them were negative, I would say the improvement is what? Worth. It's not actually improvement. Any questions? Is it clear? Okay.
I had a question about the conclusion.
Sure.
Would you just say there's no difference between them?
Yeah.
Okay.
Okay. Hypothesis testing. So sometimes, so we know that like if we get a sample, we can have point estimates, and then said point estimates are not good, okay, because they don't capture the variability. That's why we came up. Actually, we used basically confidence interval. We say, okay, instead of using just one point to estimating a population parameter, use an interval, and with some confidence you can say the true parameter belongs to this interval. Okay? Now, sometimes we want to basically check a claim about our parameter of the population. Okay? For example, we want to see if, in this example, the percentage of non-conforming part is less than a number or not. Okay? So if we want to check a claim about the population of the the parameter of the population, then we use a statistical hypothesis testing. Okay? So it's basically we make some hypothesis first, then we use sample to test whether those hypotheses are correct or not, statistically. Okay? For example, we want to see if mu is equal to some number, the average of a normal population is equal to some number or not. Okay? Let's say a supplier says that so you have some standard limits, okay? Lower standard limits and upper standard limits. Let's say this is for a part, a manufactured part. Let's say this is a manufactured part, and the length should be between 20 and let's say 24, and the target is what? 22. This is your target. Okay? And you have a supplier. It tells you that my process can produce parts which are on average 20. Okay? Parts 20 inches, let's say. Oh, I'm sorry, 22, which is your target. Then I want to see if his claim is correct or is not right. So what should I do? I go to his process, I collect a bunch of parts, I measure them, I calculate some X bar, some S, and then based on that I want to see if this is correct or not. Okay? Is it clear what do I mean by hypothesis testing? I think some of you have seen this before. So we have two hypotheses. One is H null or null hypothesis, and the other one is alternative. Okay? Sometimes we denote this by H sub A, and sometimes by H1. Okay? Both of them are used. This is one example. As I said, we have a population, we get a sample, and then we make some conclusion. The conclusions are like this. Null hypothesis is rejected. Null hypothesis is not rejected. Okay? Do we say we accept null hypothesis? No. We said is rejected and not rejected. Do you know why? Maybe some of you have seen this before. Why we say either is rejected or not rejected. We don't say it's accepted.
You have to measure the entire population to be able to...
Exactly. Because you get a sample. Okay? This sample cannot provide evidence for rejecting your null hypothesis. Okay? But maybe if you collect another sample, gives you this basically evidence to reject the hypothesis. If you want to say I accept, because we know that like there is some error associated with sampling, random sampling. If I want to basically have no error, then what should I do? I should measure the entire sample. Okay? The entire population. Okay, this is another example for the variance. And as I said, a statistical hypothesis test is a statement about the parameters of one or more populations. And here is one example. You can see, we want to see if, let's say, mu is equal to 50 or not equal to 50. What we do, we collect a sample, we calculate x bar of this sample, and then we have some limits. Okay? If this x bar is between these two limits, we said we fail to reject H null. If it is beyond these two limits, either from the lower one or above, basically the upper one, then we reject H null, and we said mu equal to 50 is wrong. Okay, it's not true. Does it make sense? Yep, go ahead.
Do you know why it's called null hypothesis?
Not really.
The reason for that?
No. That's a good question. I don't know. Yeah. Maybe we can Google it. Why they call it null hypothesis. Yeah. Anyways, so if we have like two bounds. So the question is, how can I come up with these two upper and lower bound? Okay. So that's what we are going to learn. How we basically define the lower and upper bound. But do you have any idea if I ask you to suggest basically something to guess how we can basically find this lower and upper limit, what would you come up with? What would be your suggestion?
Confidence intervals.
Confidence intervals, no? And you will see it's related to that. Okay. So two-sided alternative hypothesis test. So we have two types. One is one-sided, the other one is two-sided. If your alternative is inequality, okay, like in form of mu is not equal to 50, then we call it two-sided because it could be either greater than 50 or less than 50. If it's in form of less than or greater than, we call it one-sided. Sometimes we want to check only the upper limit of that. For example, mu is less than 10. For example, customers waiting time in a bank. Okay, we care about the upper limit, not the lower limit. Another example is for the lower side, not upper side, time to failure of machines. The higher, the better. Okay? So, you have a question?
Yeah, so for the one-sided, for H naught, for like mu equals 10, if you're only doing one-sided, is that also saying that like H naught is also saying that it's just not their alternative?
Yeah, exactly. So the thing is, okay, that's actually a good point. This is basically, we always use equality in H naught, okay? And so, for example, 50 or not equal to 50, okay? If you are talking about one-sided, like this, then still we use equality here, but implicitly we are saying mu greater than equal to 50. Okay? But in terms of notation, we use always equality in H naught. And the reason is when we are talking about type 1 and type 2 error, okay, this is considered as type 1 error, and we have different type 1 errors, and this one the equality maximizes type 1 error. So we care only about this guy, not greater than that. Okay, but implicitly, yes, it's basically mu greater than or equal 50. Is it clear? That was a very important question. So we always use the notation of equality in H0, but when we are using one-sided, implicitly we are using greater than equal, but we show as equal. Yeah.
Is there any kind of like standard? So if we want desire a short waiting time,
that's a very good
we
question.
set it up
Yeah.
like the left one.
So another important, basically, let's say agreement. Let's say like this is conventionally we do it like this. Always put what you claim, okay, and what is desired in H alternative, okay. So for example, if you want to have customers waiting time in a bank, okay, we want this to be a small. So we set a smaller than 10, and we put it in H alternative, okay. For example, time to failure of machines, we want to be larger than a number. And this number, I want to test if it is 10 or like 100 or not, then I put in my H alternative, my H null going to be equal to 100. So two things. One, put the claim or desire basically property or characteristic an H alternative. And the second one, H null is always equality, okay, when you show it. But implicitly, it implies the opposite inequality, opposite of H alternative, actually. Yep.
So in the two-sided case, what we actually want is mu not to be 50?
No, this one is different, okay? So this one is basically, this is only for one-sided, the one I said. For basically target, we said mu is equal to 50 or it is not. Okay? That's it. This is the desired one. Yeah, that's basically, I would say, one exception. What I said in terms of desire or claim is in H alternative, in one-sided, not two-sided. Any other questions? Is it clear the difference between the meaning of hypothesis testing, the difference between one-sided and two-sided, and how we basically show them in terms of equality and inequality? Good? Okay. So how we can basically do a hypothesis testing? Let's start with design. There are two phases, design and use. The first one is design. First of all, state the null and alternative hypothesis. So, and specify the sample size and significance level, which is, significance level means alpha, which is 1 minus basically confidence level. One example, we want to test a mean of normal population with sigma squared equal to 4. So we want to do this test, whether mu is equal to 50 or not. N is 5 and alpha is 0.05. What is the second step? Define your test statistic. So by test statistics, I mean, if I want to check mu, then I need to use X bar. Am I right? And maybe I use X bar. Maybe I use a function of X bar. In this case, I can use the standardized version of X bar, which is called test statistics. Subtract mu, and this mu is what? Should be this guy, divided by standard deviation. The third one is find the distribution of the test statistics and the rejection region. So what is the distribution of your test statistics? And this should be actually, you can add one sentence here, under H null. So what is the distribution under H null? Then find the rejection region. So actually what I mean is your Z, X bar minus mu divided by this guy. So under H null, what's going to happen? I can replace this mu with mu naught. Then I know that this guy follows a normal distribution with mean 0 and a standard deviation 1. And based on that, I can define my rejection region. Okay? And that's easy. Why? Because basically, if mu is equal to mu 0, okay, if this is true, then this distribution should be a standard normal. So what does it mean? If it is a standard normal, then I need to find two limits, okay, that so that basically two limits to define the rejection region, okay. If it is a standard normal, then what is the probability of, let's say this is lower limit and upper limit. What is the probability of z belongs to this interval? I can find it based on normal distribution, based on the value of UL, okay? So if I define this as z alpha over 2, and this one as minus z alpha over 2, then what is this probability? 1 minus alpha, okay? So what does it mean? It means if your mu is actually 50, or mu 0, then probability of not rejecting your H null, because it's in between, is 95%, which is a good number, okay? So you usually define your rejection region when your Z0 is greater than Z alpha over 2, or Z0 is less than minus Z alpha over 2, okay? This is just one example. How we come up with rejection region for different scenarios is basically another story for the next slides. But is it clear what I mean by rejection region? So when your basically test the statistic value is in the rejection region, you reject H null. So hypothesis testing, the second phase is use. This is just a design, okay? I haven't observed anything. I just designed my test. Collect the sample. That's the fourth step. So I collect a sample, let's say, from the population. I calculate X bar. I calculate my Z, the Z value, and then I compare it with rejection region. If it is higher than rejection region, if it falls in the rejection region, then I reject H null. In this case, 145. Is not greater than 1.96, then we make the decision H null is not rejected, or mu is equal to 50. Or we cannot reject mu is equal to 50. Questions? Is it clear? So first we design, second we basically use this procedure. Okay, let's just start with the first scenario. We want to do hypothesis testing for the mean, and alternatives are here. Okay, we have one side, two-sided alternatives, and one side, two one-sided. Okay. Now, okay. For the first one, I show how to come up with the limit, why it makes sense to basically come up with the limit, and then with these limits, with these rejection regions. And basically, then you can do basically similar, you can follow the similar procedure to find the limits for other conditions and scenarios. So let me start with the two-sided one. Mu equal to mu 0, and mu is not mu 0. It makes sense that I collect a sample and get X bar. So what would be basically a logical procedure? I use X bar. I know that this X bar coming from a population with mu, and I have no idea if this mu is exactly mu 0 or not. So what should I do? I can construct a confidence interval based on this X bar and see if this mu 0 belongs to that confidence interval or not. Does it make sense? Okay? In order to test this hypothesis, what I can do, I can collect a random sample, get the X bar, use this X bar to construct a confidence interval and see if this mu 0 belongs to this confidence interval or not. Does it make sense? Okay. So confidence interval based on X bar. The lower limit is X bar minus Z alpha over 2. And the upper limit is X bar plus Z alpha over 2. Okay? So if mu is greater than u, which is this guy, what should I do? Reject, I'm sorry, if mu 0. Reject H naught. Okay? So it's basically something like this. I know I have X bar here, and I have a lower and upper confidence interval. So if your mu 0 is here, if it is your mu 0, I do not reject. But if your mu 0 is here or here, we reject that. Does it make sense? Because the X bar that you get does not provide the evidence that mu belongs to this confidence interval. Is it clear? Any questions? Okay. Now, I want to show you how we can go from this to that criteria, critical values or rejection regions. It's actually very simple. The other one is mu 0 less than L, which is X bar minus Z alpha over 2 sigma. This is basically reject H naught. I continue up here. So what I'm going to do, I am doing some simplification here. So taking X bar to the other side and divided by sigma squared divided by square root of n. And the same thing here. Okay? So mu 0 minus X bar, this is less than, is that correct? Yes. Let's multiply it by negative. Okay. I guess I'm making a mistake here. Oh, yeah, no, that's correct. Sorry about that. Okay? So if this guy is greater than Z alpha over 2 or less than this, then what I do is reject H null. Yeah. So basically what it says, if this guy is less than Z alpha over 2, we do not reject H null. If it's greater than Z alpha over 2, we reject H naught. Okay? So it's basically based on the confidence interval that you have. Intuitively, I can say I develop a confidence interval, then I check whether mu belongs to this confidence interval or not. If mu does not belong to this confidence interval, I should reject. This is basically what I have. If mu does not belong to this confidence interval, which means greater than the upper limit or less than the lower limit, then I need to reject that. Okay, otherwise I should accept. So it's basically the standardized distance between x bar and mu 0. Standardized distance. What I mean by standardized, it's divided by a sigma divided by square root of n. Okay? So the distance, it doesn't matter. When we are talking about distance, the positive and negative sign doesn't really matter because it's basically symmetric. Okay? And so I use the absolute value. So if the distance between x bar and mu 0 and the standardized distance is less than this guy, I reject. I do not reject, otherwise I reject that. So now, do you remember what was the confidence for that? This was 1 minus alpha % confidence interval. So the confidence for this guy is 1 minus alpha confidence, and alpha is called significance level. Okay? So confidence level and significance level. That's confidence, and the other one is significance. Is it clear? Any questions? The concept is clear. How we derive basically this critical region. So you can do the same for the one-sided one. Okay? So what you do, you calculate x bar, you calculate z0, and then compare it with these two thresholds. Greater than the thresholds, reject, otherwise we cannot reject. That's it. And something to remember, the inequality, the inequality direction for the alternative and critical region always the same. You see that? So this is greater than mu 0, this is greater than z alpha. This is less than mu 0 is less than minus z alpha. Any questions? Okay. One example. Be faster. So we have calculated the burning rate, I think. Yes, the burning rate of using basically 50. The specifications requirement that the mean burning rate must be 50 centimeters per second. And so basically this is the target. We want to see if our process is like that or not. We know that the standard deviation of the burning rate is 2 centimeters. The experimenter decides to specify a type 1 error probability or significance level. I will tell you later why we call it type 1 error as well. Significance level of alpha equal to 0.05. We collect a random sample, 25, and this is the x bar. So it's very simple. Based on the problem statement, it's two-sided. We just want to see if it is equal to 50 or not. So is it 50? Yes, centimeters. The second one says it's not 50. Our x bar is 51.3, n is 25, and alpha is 0.05. So we calculate z0, and sigma is also given. Standard deviation is 2. Why z0? Because I'm testing mu with known standard deviation. That's why I'm using these test statistics. X bar minus mu 0 divided by sigma divided by square root of n, which is 51.3 minus 50 divided by 2 divided by 25. This number is 3.25. So what is the threshold? Z alpha over 2. In this case, alpha is 0.05. Is 0.05 divided by 2 is 1.96. So what is the conclusion? The absolute value of this guy is greater than 1.96. This is basically 3.25. Therefore, we reject H null, which means mu is not 50. Okay? Is it clear? Any questions? Are we good? Okay. Second example, I'll give you a couple of minutes to work on that. So it's about the response time of a distributed computer system. So the most important thing, I mean, everything is very standard. So you need to know whether you are talking about mean or variance, and then if you are talking about mean, whether the variance is unknown or known, and then this is very standard. And you know like how to calculate your test statistic. The most important part of it to understand and to realize whether it's one-sided or two-sided, and if it is one-sided, is it greater than or less than?
Can we choose any significance level?
Oh, that one is 0.05. Yeah, if it's not given, the default is 0.05. So alpha here is 0.05. Okay. So what is our claim, or what we want to investigate is the mean response time greater than 75. Okay, so we put it always where? On H alternative. And what is our H null? Equal. So if we reject H alternative, H null, then we can say it's greater than 75. Okay. So we collected a sample, which is basically executing one command 25 times, and the X bar for this sample is 79.25, and we know that sigma is 8. So actually from past experience, from historical data, it is known. These are the keywords for variance is known, or a standard deviation is known. Okay? So again, from past experience, based on historical data, or it is known that. These are the keywords that says, I already know the variance. I'm not estimating the variance. Okay? This is very important in exam and homework. You will basically, because if you are estimating instead of Z, you need to use what? T-distribution. So it says, from past experience, so I know this is sigma, not S. Z0 is x bar minus mu, 0 divided by sigma square root of n, which is 79.25 minus 75 divided by 8 divided by the square root of n. This number is 2.566. And we know that the critical region is what? This guy. So the absolute value of Z0 is 2.566. Alpha is 0.05. And Z of alpha over 2 is 1.96. So this is greater than, therefore we reject H null. Okay? Why? Because of this. You can see that. Z0 greater than Z sub alpha, then we reject H null. So we reject H null.
Is there a reason why you did alpha over 2?
Oh, yes. I made a mistake. Yep, sorry. 1.645. Doesn't change the conclusion though. But you're right. 1.645. Z of 0.05. Yeah.
I didn't know the Z is to remember. I think you've said this. Did I look for 95% in
The absolute value is not here. Sorry about that. Go ahead.
What the Z score is? Would I look for the 9.95 in the table and find which? I didn't know what.
So what do you're talking about this guy?
Yeah.
So this means that you need to find A such that phi of A is 0.95 from the table. Find A such that phi of A is 0.95. This gives you Z of 0.05. Okay? Again, we calculate Z0 based on what you have here. The critical region is Z0 greater than Z alpha. So Z0 is 2.566. Z alpha is 0.05. This is your Z alpha greater than, reject H null. And mu is basically the mean time exceeds 75. Any questions? Sorry, I went over time. I'll see you on Wednesday.